Okay, 2013, step 1, question 4, calculus question again. So, show that for n greater than 0, the integral from 0 to a quarter pi tan to the nx sec squared dx is 1 over n plus 1. Okay, that's just a classic A-level integral, isn't it? Because it's derivative present, right? You know, if you differentiate tan, you get sec squared. Yeah? So this could directly become what? This equals... okay, I could integrate immediately, really. What's this? 1 over n plus 1 times tan n plus 1 x. Yeah, and you can check, right? If you differentiate that thing, you know, by chain rule, you get the second secant squared there, which you sort of want, right? Quarter pi 0. Which is 1 over n plus 1, right? Trivial. Okay, the first part was quite chill. How about the second part though? This time I have to reverse. You know, I have a tan here. So I have what is this? How could I write this in a nicer way? Do we all know how to differentiate sec? We should, right? Although, you know, we don't have a formula book in STEP, but we should know these things in our head, right? Or if you really don't know how to differentiate sec, you could always go 1 over cosine and differentiate using the quotient rule, product rule, whatever rule you like. Yeah? So you could go 1 over cosine and differentiate that if you're not sure. Okay, but I could say that sec differentiates to sec tan. So how about we write it like this? So I have a sec x tan x. Okay, I haven't done any dodgy, right? I haven't done anything dodgy. I just took out one of the sec x's and I put a bracket around them. Okay, so now again, this is derivative present, right? This is derivative present. So what can I do? What can I do? Well, I could integrate properly, i.e. 1 over n sec to the nx quarter pi 0. All good? And if I add the limits here, what is sec of a quarter pi? Sec quarter pi is, what is it? I actually don't know what it is. What would it be? Root 2, right? So this is root 2 to the n. Yeah, over n. Minus, if I chuck in 0 here, what is that? Sec of 0 is always 1, right? So this is minus 1 over n, and that's as required. Okay, so the first part shown. Now let's look at the second part. Evaluate the following integrals from 0 to quarter pi, x times some sort of thing. Now, what would our intuition be? I have some algebraic expression, which is the x, multiplied by some trig expression, which was literally part 1. Well, then the sensible thing to do is by parts, right? And you want to differentiate the x to get rid of it. Right? Okay. So, what are we doing here? Let me erase this. So, let's do this by parts, shall we? So, what have we got? What have we got? So, this equals 0 to quarter pi of what? Okay, let's do the by parts straight away. So, I'm going to differentiate the x and I'm going to integrate the bit behind, okay? So, how do I do my by parts? X times what? What is this thing, remember? How do I integrate this thing? This thing is in the form this, right? This is just a quarter sec to the 4x, as I explained before, okay? Minus integral of quarter sec to the 4x, and you differentiate x becomes 1, right? So we don't have to take care of that. And what is this? This is just dx, is it? Like that. Yeah? And how do I integrate a second to the 4? How do I do that? Well, this is, okay, whatever the first bit is, minus, this is always, the technique is sec squared x, and then sec squared x minus 1, okay? This is always the technique. Tan squared x minus 1. Is it? Yeah, plus 1. Okay, I'm being silly. Tan squared x plus 1 is sec squared x, right? And you know how to integrate this, right? You know how to integrate this by part 1, right? You have this, and you have that, right? This bit is for the 1. Is it? No, the other way around, right? Okay, you could use, but both of them use the first one, right? Because, you know, chuck in n equals to 2 and chuck in n equals to 0. Here, right? And you could evaluate the last bit here. Yeah? Not the hardest, I suppose. Okay, now let's go for the next one. Well, the next one's sort of the same thing, actually, you know. We have x squared this time instead of x. Right? So maybe by parts 2 times would be a sensible idea. Let's try that. So, again, I'm just going to go straight into the by parts, okay? This is, I think it's easy enough to see straight away. Okay, so that equals what? X squared times what? Okay, how do I integrate this? Remember, this is just what? A half tan squared, right? And minus what? Minus I differentiate the 2x gives me differentiate x squared gives me 2x. Yeah, and now I have a half tan squared x dx. Lovely. Okay, so now the nice thing is that the 2 and the 1/2 sort of cancels out, which I like, right? So I get whatever the first bit is, minus x times tan squared x dx. Right, and again, now I have x now, so I could do it by parts. Right? So how would I do this? This equals, let me erase this quickly. It's taking ages to go away. Okay, there we go. Minus what? X, how do I integrate tan squared? You change tan squared into sec squared x minus 1. That's always a technique, right? Then you can integrate, right? You can integrate sec squared, which gives tan. You can integrate the minus 1, which is minus x. Lovely. All right, subtract. Now, if I differentiate, the x gives me 1, right? So I'm left with tan x minus x dx. Okay, I'm sure we're more than happy with this integration. All right, if you tell me you don't know how to integrate tan x, then you just go sine over cosine and then think about it, right? That's how you do it when you're unsure, right? Because you don't have a formula book. Okay, and you chuck in the limits properly, okay? I'm not going to do the exact calculation, no point. All right, but it's quite a nice question. All right, there's good calculus involved there. All right, so there you go.